This is the third video on Chapter 42, Solids of Revolution and Surface Area. And this is the last example that I'm going to do from this chapter. This example was one of the favorite examples that we looked at when I was a freshman in calculus class. And all these years later, now that I'm a math professor, it's still one of my favorite examples to teach. So we look at the function y equals 1 over x from 1 to infinity. So this gets closer and closer to the x-axis but never quite touches it. And if we look at this region as an infinite region on the plane, and we want to calculate its area, we integrate the function. So we integrate 1 to infinity of 1 over x dx. We've done this integral before. So we calculate the limit as t goes to infinity of the integral 1 to t of 1 over x dx. To save some board space and some recording time, I took a shortcut and just wrote this as a limit as t tends to infinity of natural log of x evaluated at t and evaluated at 1. Natural log of 1 is 0, so this is equal to the natural log, and the limit as t tends to infinity of the natural log of t, which is infinity. It doesn't surprise us that this has an infinite area. Another thing that probably doesn't surprise us is that it will also have an infinite surface area. So if we look at the integral from 1 to infinity, I said surface area. What does that mean? So we take this and we rotate this about the x-axis. And now it makes a three-dimensional object of infinite length, and this is called Gabriel's horn. So that's what this object is called when you rotate this about the x-axis. And now we want to look at what the surface area of Gabriel's horn will be. So we integrate 1 to infinity of 2 pi times our function, 1 plus the derivative of the function squared under the square root. Remember, the derivative of 1 divided by x is negative 1 divided by x squared. So when we square that term, we have 1 divided by x to the fourth. So we're integrating this function. Now, we're not actually going to integrate this. We're just going to use the comparison theorem to show that it diverges. 1 divided by x is less than or equal to 2 pi times 1 divided by x times some expression that is greater than 1. So this inequality is fairly easy to see, and because this improper integral diverges, this improper integral diverges by the comparison theorem for improper integrals. So again, it doesn't surprise us that this will have an infinite surface area. Think about what that means. If you're going to try to paint the outside of this, and it wouldn't even matter what the thickness of your paint is, assuming it is a constant thickness all the way through. If you turn the oceans to paint, you could not paint the outside of this. Here's the surprising part. Let's look at the volume of Gabriel's horn. So volume was something we learned in Calculus 1. We just integrate pi r squared, or pi times f of x squared, which we thought of as pi r squared. And so we integrate 1 to infinity of pi times f of x squared. 1 over x, 1 divided by x squared is, well, this is the integral 1 over x to the p, where p is greater than 1. So we know that this converges, but not only that, we can actually calculate this integral. So again, this is a limit as t tends to infinity of the integral from 1 to t of this function. To save time and to save space, I've just taken a shortcut here. So we have pi times the limit as t tends to infinity, antiderivative, negative 1 divided by x, evaluated at 1 and evaluated at t. Limit is, so we just substitute 1 and t right here. We simplify this. So we have pi times the limit as t tends to infinity of 1 minus 1 divided by t. 1 divided by t goes to 0. So we have pi times a limit of something that goes to 1. So this limit is just pi. So that means the volume of Gabriel's horn is pi. So you can fill this thing up with pi units, whatever you're measuring your volume with, which is a little bit greater than 3 and a lot less than 4. But yet the outside of it has an infinite surface area.